In the previous module, we discussed unconstrained optimization, in which we chose best alternative available of the dependent variable corresponding to a particular value of independent variable. This module is thus a continuation of the previous one, but in the previous module, choosing optimum value of the dependent variable was not a constraint, but in this module, choosing optimum value of the dependent variable is constrained by some constraint function. A constraint is anything that prevents the system from achieving its goal. There are many ways that constraints can show up, but a core principle within the theory of constraints is that there are not tens or hundreds of constraints. There is at least one, but at most only a few in a given system. Constraints can be internal or external to the system. An internal constraint is in evidence when the market demands more from the system than it can deliver. If this is the case, then the focus of organization should be on discovering that constraint and following the 5 focusing steps to open it up and potentially remove it. An external constraint exists when the system can produce more than what the market can bear. If this is the case, then the organization should focus on mechanism to create more demand for its products or services. An optimization problem consists of maximizing or minimizing a real function by systematically choosing input levels from within an allowed set and computing the value of the function. In microeconomics, the utility maximization problem and its dual problem, the expenditure minimization problem, are economic optimizing problems. Insofar as they behave consistently, consumers are assumed to maximize their utility, while firms are usually assumed to maximize their profit. Also, agents are often modeled as being risk averse, thereby preferring to avoid risk. Asset prices are also modeled using optimization theory, though the underlying mathematics relies on optimizing stochastic processes rather than on static optimization. Trade theory also uses optimization to explain trade patterns between nations. The optimization of market portfolios is an example of multi-objective optimization in economics. Economic decisions are the result of an optimization problem subject to one or series of constraints. Consumers make decisions on what to buy, constrained by the fact that their choice must be affordable. Firms make production decisions to maximize their profit, subject to the constraint that they have limited production capacity. Households make decisions on how much to work, play, with the constraint that there are only so many hours in the day. Firms minimize costs subject to the constraint that they have orders to fulfill. All of these problems fall under the category of constraint optimization. The solution of a constraint optimization problem can often be found by using the so-called Lagrangian method. In general, the Lagrangian method is the sum of the original objective function and a term that involves the functional constraint and a Lagrange multiplier lambda. The Lagrangian method is based on the sufficiency theorem. This means that method can work but need not work. Our approach is to write down the Lagrangian, maximize it, and then see if we can choose lambda and maximizing x so that the conditions of the Lagrangian sufficiency theorem are satisfied. If this works, then we are happy. If it does not work, then too bad. We must try to solve our problems in another way. After studying this module, you shall be able to know the meaning and definition of constraint optimization, find out value of variable within given constraint, understand the Lagrange multiplier and the Constraint condition. Now we will be discussing the meaning and definition of constraint optimization. Constraint optimization is the process in which we try to find out maximum or minimum value of dependent variable within the given constraint. Under constraint optimization, we have an objective function which is either to be maximized or minimized. Like first, the utility function, which is denoted by u, is a function of xy. Second, output function denoted by q is a function of kl. Profit function denoted by pi is a function of rc. Utility function of consumer is constrained by the household income. Output function is constrained by the resources available, generally cost, which is with the producer. And the profit function is constrained by the cost and output both. Equality constraint. Under this, we assume that all income of households is to consume goods and services. All resources of producer is used to produce goods and services. In short, we can say that under equality constraint, there is no saving. Now we will be talking about utility maximization. Let the utility of the consumer be a function of two goods x1 and x2. That is, u is a function of x1 and x2. This is known as equation 1, which is known as the objective function. Let the consumer have M money income, which has to be spent on two goods x1 and x2. That is, M is equal to P1 x1 plus P2 x2. We denote this as equation number 2, where P1 and P2 are unit prices of good x1 and x2 respectively. To optimize the objective function, we may use the Lagrangian multiplier method as follows. L is equal to u x1 x2 plus lambda bracket open m minus p1 x1 minus p2 x2. This is denoted as equation number 3, where L is the Lagrange function. X1 x2 are two goods, lambda is the Lagrangian multiplier, p1 and p2 are price of goods x1 and x2, and m is the money income. From equation 3, through the Lagrangian multiplier, we have to find out what value of x1 and x2 within the given constraint. M is equal to P1 x1 plus P2 x2. Maximize the utility U. For this, we differentiate the equation 3 with respect to x1 and x2 and equate it to 0 for the first order conditions. L is equal to U x1 x2 plus lambda bracket open M minus P1 x1 minus P2 x2. dl by dx1 is equal to fx1 plus lambda p1, which is equal to 0, denoted as equation 4. dl by dx2 is equal to fx2 plus lambda p2, which is equal to 0, which is denoted by equation 5. dl by d lambda is equal to m minus p1 x1 minus p2 x2, which is equal to 0, which is denoted by equation 6. For critical value of x1 and x2, dividing equation 4 by 5, we get fx1 over fx2 is equal to p1 by p2, which has been denoted by equation 7. We know that fx1 by fx2 is also known as marginal rate of substitution x1, x2. That is, for equilibrium, MRx x1, x2 is equal to P1 by P2, where MRS is the marginal rate of substitution. To find out whether ratio of equation maximizes the utility or not, this may be checked by the border Hessian condition, in which we use constraint as border in matrix as follow. So in the border Hessian constraint is used as a border, we have the border Hessian constraint, which is equal to 0 minus P1 minus P2 minus P1 fx1 x1 fx1 x2 minus P2 fx2 x1 fx2 x2. If the border Hessian constraint is then equal to 0 minus P1 minus P2 minus P1 fx1 x1 fx1 x2 minus P2 fx2 x1 fx2 x2, which should be less than 0. Then it represents minima. If the border Hessian constraint is equal to 0 minus P1 minus P2 minus P1 fx1 x1 fx1 x2 minus P2 fx2 x1 fx2 x2 greater than 0, then it represents maxima. This can be explained with the help of a simple diagram. In the diagram, AB is the budget line, which represents the price ratio. IC is the indifference curve. EO represents equilibrium, where slope of IC and slope of budget line are equal, which represents the optimum consumption of x1 and x2. These are x1 raised to the power of O and x2 raised to the power of O. Now we will be discussing the output maximization. Let the output Q be a function of two factors of production, labor L and capital K. That is, Q is a function of KL, which is represented by equation number 8, where Q is the output, K is the capital, L is labor. Assume C is the total resources available with the producer, which may be used to employ capital and labor. Therefore, the constraint with the producer is C is equal to PL into L plus PK into K, where PL is the price of labor and PK is the price of capital. In order to maximize the output with given constraint, students may use the Lagrange multiplier, where production function is the objective function and cost function is constraint function as follows. Z is equal to a function of KL plus lambda bracket open C minus PL into L plus PK into K bracket close, which is represented by equation number 9. Differentiating equation 9 with respect to capital labor and lambda and equating it to 0, we get del Z by del L is equal to MPL minus lambda PL, which is equal to 0, denoted by equation 10, del Z by del K, which is equal to MPK minus lambda PK, which is equal to 0, denoted by 11, del Z by del lambda is equal to C minus PL into L plus PK into K, which is equal to 0, denoted by 12, where MPL and MPK are the marginal productivity of labor and capital respectively. Now dividing the equation 10 by equation 11, we get MPL by MPK is equal to PL by PK, which is again denoted by equation 13. Thus equation 13 states that for output maximization, the marginal rate of substitution should be equal to factor price ratio. Now we will be talking about profit maximization. As we know that profit is surplus of revenue over cost, and revenue and cost both are functions of output. Let the profit function be profit is equal to RQ minus CQ, which is now denoted by equation 1. Differentiating 1 with respect to Q, we get E profit divided by DQ is equal to MR minus MC, which should be equal to 0, or MR is equal to MC, which we denote as equation 2. Equation 2 states that profit maximization, marginal revenue MR should be equal to marginal cost MC. Example 1, utility maximization. Let the utility function be u is equal to x raised to the power of 0.5, y raised to the 0.5. This is called equation 1, where u is utility and x and y are two goods. Money income of consumer is 200, price of x is 2 and price of y is 2. Then the constraint function will be 200 is equal to 2x plus 2y. This is called equation 2. Using Lagrange multiplier, L is equal to x raised to the power of 0.5 into y raised to the power of 0.5 plus lambda bracket open 200 minus 2x minus 2y. This is called equation 3. Differentiating with respect to x, y and lambda, we have del L by del x is equal to 0.5 x raised to the power of 0.5 into y raised to the power of 0.5 minus 2 lambda equal to 0, known as equation 4. dl by dy is equal to 0.5 y raised to the power of 0.5 x raised to the power of 0.5 minus 2 lambda equal to 0, known as equation 5. dl by d lambda is equal to 200 minus 2x minus 2y, which is known as equation 6. Dividing equation 4 by 5, we get y divided by x is equal to 1. Hence y is equal to x. That is, the consumer will consume both goods in equal quantity. Substituting y is equal to x into the constraint equation, 200 is equal to 2y plus 2y, which is 200 is equal to 4y. Y is equal to 50 equal to x. That is, optimum consumption will be 50, 50 of each good. Example 2, output maximization. Let the production function be Q is equal to K raised to the power of 0.2 into L raised to the power of 0.8, which is known as equation 1, where K is capital, L is labor. Let the producer have 500 to spend on capital and labor. Price of capital is 2 per unit and price of labor 4 per unit. Then in order to maximize output, Lagrange multiplier should be used as follows. Z is equal to K raised to the power of 0.2 into L raised to the power of 0.8 plus lambda bracket open 500 minus 2k minus 4l, known as equation 2. Differentiating equation 2 with respect to k, l and lambda, we have del z by del k is equal to 0.2k raised to the power of minus 0.8 into L raised to the power of 0.8 minus 2 lambda equal to 0, known as equation 3. Del Z by del L is equal to 0.8 K raised to the power of 0.2 into L raised to the power of minus 0.8 minus 4 lambda equal to 0, which is known as equation 4. Del Z by del lambda is equal to 500 minus 2K minus 4L equal to 0, which we denote as equation 5. Dividing equation 3 by 4 and substituting in 5, we get 1/4 K divided by L is equal to half. K by L is equal to 2. That is, in order to maximize output, labor and capital should be used in 2L is equal to K ratio. With the discussion, we can conclude that constraint optimization is one of the important tools, and by using it, we can find optimum consumption, optimum use of resources.